Hello and welcome to episode 3 of Look Up Tonight with the Orange County Astronomers. Our program tonight features highlights from the July meeting of the Orange County Astronomers at Chapman University. Jim Benet, who is our outreach coordinator, gave a highly entertaining and informative presentation full of the viewing tips on the night sky in July and August. Our main speaker tonight is Dr. Michelle Thaller, who is a research scientist and manager of the SIRTF Education and Public Outreach Program. What is SIRTF, you're probably asking? SIRTF stands for the Space Infrared Telescope Facility, which is a brand new space telescope scheduled for launch in August of this year. Our program will also feature other interesting segments showing the OCA's observatory facility near the town of Anza, California, where members, their guests, and the invited public can view the skies through the club's 22-inch computerized telescope and many other telescopes our members bring along to the monthly star parties. So let's begin the program with a segment from the What's Up presentation by Jim Benet. Here, Jim starts his program in a very unusual but nevertheless interesting way.
Okay, here we go. This is what it was. Summertime, and the clusters are easy. Mosquitoes biting, and the galaxy's high. Your scope is rich, and your mount is good looking. So hush, little baby, and look to the sky. Okay, Mercury, and that's rising higher in the west after sunset, but it's still a little low. It'll reach its peak kind of toward the end of the month. So look for Mercury, and don't look into the sun while you're trying to do that. Venus, of course, is in the morning sky. It's very close to the sun, but it's heading back our way, and it's heading back toward the sun. And I think next month or next month after that is going to be switch back to the evening sky. So let's go. So actually there's going to be, not this month, but next month, there's actually 3 planets that are at opposition, and Mars is the key. Everybody's getting all excited about Mars. We got Mars. Right now it's something like a magnitude minus 1.8. You got to get up. It rises around midnight, but it looks better, at 2 o'clock in the morning right now. It's in the constellation Aquarius. And the thing to watch now is on August 28th, it'll be the closest to the Earth, and not only the closest to the Earth for this go-round. We see it about every 26 months. We get real close to it, and it won't be this close again for another 278 years or 275 years. So it is an excellent time to watch that.
Remember what Jim said about Mars? Towards the end of August will be the best time to look at Mars through a telescope, and there will be lots of public activities by our club and many others focusing on Mars. Please check our website for further information on related events. Now on to highlights from our main presentation by Dr. Michelle Thaller of Caltech JPL. As part of her amazing presentation, Michelle brought along her $50,000 professional infrared camera. She used this to demonstrate the principles of infrared astronomy by getting help from the audience. Let's watch.
But what I wanted to start with today was topics of infrared astronomy. What are we doing using an infrared space telescope? And SIRTF in many ways is a corollary of the Hubble. It's a multi-year space telescope mission, but instead of seeing invisible light and a little bit into the infrared like Hubble does, SIRTF will see from 2 to 180 microns, the entire range of infrared light. And so tonight I'm going to talk to you about what we're going to be looking for with an infrared telescope. And then if we have time, I even have some brand spanking new launch animations to show you how we think the telescope will be operating in orbit, but we'll see if we get to that. But before I start my astronomy talk, I wanted to talk to you a bit about infrared light in general, because oftentimes it's a little difficult to visualize what you're looking for with invisible types of light. And so I brought my infrared camera. They don't have to be all the way off. But what you're seeing when you look through an infrared camera is quite simply a thermal image. The lighter regions are areas that are warmer, and, oops, I'm getting away, and the regions that are colder are darker. So you'll notice that people's noses often are darker than the rest of their face. Eyes and mouths tend to be quite warm. So I kind of pan around. Everybody has a slightly different heat signature. Everybody looks a little bit different. I wanted to show you something because this is one of my favorite tricks with the infrared camera, and you can't always do it unless somebody has a good thick mustache. Now, what I'd like you to do is just breathe up into your mustache. There we go. The fire-breathing dragon there. The infrared camera can detect the heat that's trapped in the air in his mustache. It's a very good insulator. So whenever I see somebody with an excellent mustache, I always, thank you very much. Okay, I want to do a couple more demonstrations, and maybe I'll get a few victims that are a little bit easier to bring up to the camera. Could I ask you? Would you come up and see yourself in the camera? Yeah. Now, you wouldn't mind holding an ice cube, would you, if I gave you an ice cube? Okay, let me get an ice cube. Hold on a second. Okay, if you notice, my hands are actually pretty dark because I was holding ice before, but I'd like you to hold your hand up and let the ice... Yeah, the cold water that you see dripping down your hand is actually just it's dark because it's cold. And one of the things that I like to do that's particularly fun is if you take the ice cube, you can make your face different colors. Let me show you. If you touch it to your face, you just sort of slowly move it down. Yeah, there you go. I'm actually a very good demonstration of the camera because you can see how cold my nose is. People with longer noses, like myself, tend to have cold noses because they stand away from your body heat. So, okay, you're doing pretty good there, yeah. But you got to be a little more, should we make ourselves pirates? You know, the Pirates of the Caribbean came out. You do that? or you can get your tongue. Yeah? I'll put that one in my cup so nobody worries about that. Okay, thank you. Thank you very much. Sorry to get you wet. Okay, that's what something that's warm like a human body or something that's cold like an ice cube looks like in an infrared camera. But in reality, astronomers don't use infrared just to see something's temperature. You can tell whether something is warm or cold by using a lot of different techniques. You don't need an infrared camera to do it. The neat thing about infrared is that you can see objects that are normally too faint to see in visible light. Anything in the universe that is above absolute zero, anything that has any temperature at all, will give off some form of light. And the hotter an object is, the higher energy light it will give off. So something that, for example, is about 1 billion degrees will give off a gamma ray. That's the most energetic type of light that we know. An object that's about 100 degrees, or the temperature of a human body, naturally glows in infrared light, and that's what we're picking up here. So there are no shadows. You are emitting this type of radiation yourself. So we can see objects in space, like planets or cold dust, a lot of things that are too cool to give off visible light, but they have some temperature, and so they glow in infrared and are thus detectable. Okay, so that's a bit about infrared light, but there's a couple more things I want to show you. One of the main advantages of infrared light is that you can see through material that is normally is opaque, blocks visible light. And this is extremely important in modern astronomy because there are a lot of very interesting processes, like the stars and planets being born, that happen inside giant dust clouds, and we'll talk about that more later. Visible light does not pass very efficiently through the dust. And to illustrate that, I actually have a black plastic bag, just a regular hefty bag. And I think this isn't going to work too well for me because my hands are already pretty cold from that ice. But let me find somebody who's a little bit warmer than me. Let me go down to the... Could you put your hand inside this bag? And if you want to be particularly brave, you could even get yourself inside the bag very quickly. We'll make sure we don't asphyxiate you. If we just put your head inside the bag, or you can hold it up in front of you. That's fine. You get a form of X-ray vision, as it were, by looking at infrared light. So as he holds the bag up, you can see through it. Even though, and then yeah, the hand inside worked pretty well too. So why don't you put your hand inside again? Yeah, there it is. When you think of visible light, all of the colors from red to violet, the region that we call infrared in the spectrum of light is actually 30 times the span of what visible light is. So if visible light has all of the colors that you're used to, infrared has 30 times that range. So there's a lot of different colors to work with, a lot of different things to see. And so the images tend not to all look the same.
Now that Dr. Thaller has introduced us to the basics of infrared, she shows us various astronomical objects and how they differ when viewed through infrared light?
Now, I mentioned that the sky looks a lot different in infrared because you're able to see objects that are normally very cold, things that aren't glowing in visible light. And this is my favorite 25 words or less. Why do you do infrared astronomy? This is Orion, obviously, in visible and infrared. And the infrared was taken by the IRAS satellite, which was the last major American infrared mission, which flew in 1983. So this is real data taken by a satellite. The Orion Nebula, which I'm sure you're all familiar with, is right here. And that's actually part of a vast molecular cloud complex that's forming thousands of new stars. Lambda Orionis up here, there was a supernova or some sort of a large explosive event that actually left the shell. I believe this is the Rosette Nebula right here. So you're looking at warm areas in a dust cloud, and that's what the infrared is able to pick up. And then on the bottom there's just a little bit of a synopsis of the whole spectrum of light, all the way from gamma rays to radio. All right, now like I said, because all of these different kinds of light give you a sense of what the universe is like at different temperatures, NASA designed an entire armada of spacecraft to sample what the universe looks like in all these different ways of seeing it. We have the Compton Gamma Ray Observatory, and like I said, a gamma ray, those are only really generated by things that are in the billions of degrees, naturally. AXAF, which is renamed Chandra, sees things in the millions of degrees for X-ray. And then Hubble is visible light, things that are around 10,000 degrees, and sort of is 100 degrees and lower. We'll be able to see things even just a couple degrees above absolute zero. Now, one thing I want to tell you before I show you some more images of the infrared sky is, like I was saying, infrared is an incredibly long range of light, 30 times the span of our visible light. So when you look at infrared light, you actually may be seeing very different things depending on where in the infrared spectrum you look. This is a picture of the Horsehead Nebula, which is a dust cloud near Orion. And this is what it looks like in visible light taken by some telescopes at Kitt Peak. In near infrared, this is from the 2MASS survey, 2 micron, that's infrared, 2 micron all-sky survey. It's an infrared all-sky survey that was just completed, and the data is now all public, the entire sky. So I really recommend that you go to their database and start downloading some of these beautiful images. In near infrared, you see through the dust cloud, just like we saw through that plastic bag. And you can actually see where stars are forming inside the cloud. You can't really see the dust at all. You can't see where the Horsehead is. In far infrared, which is 7 to 15 and sort of even farther, this was taken by a satellite that the Europeans put up. When you go into far infrared, the cold dust itself begins to glow. And so you're actually seeing dust that may be only about 20 to 30 degrees above absolute zero. You see it glowing here, and that's actually the Horsehead Nebula, this little wisp. There's a newborn star right at the end of it, and that's actually what the Horsehead is. It's a cloud that's forming stars. So we're going to take a look at different types of infrared imagery. Near infrared, where you can see through things, and far infrared, where you can see cold things glowing in and of themselves. To start my story about what we're looking for with infrared, I thought I'd give you a little bit of context. And these are 2 beautiful visible light pictures of spiral galaxies. I know you're very familiar with spiral galaxies. The scale of one of these things is about 100,000 light years across. And as you can see, there's a lot of dust in the plane of the galaxy. This dark material you see here is dust. The dust is very similar chemically to what we find in this room. There's sooty stuff, carbonates, silicates. And this is a close-up of the inside of the Whirlpool galaxy. And again, look at these beautiful dark lanes of dust. That's where a lot of really interesting things are going on. The dust turns out to be very important for forming stars and planets and people. These are 2 galaxies that are merging. They're coming together, and they're probably going to form a single system, merge into one large galaxy. And they look like they're doing it pretty cleanly. They're kind of coming together. In the infrared, we now find out that these interacting galaxies are doing something quite interesting. These are 2 interacting galaxies here called the antenna galaxies. As they come together, they're mixing up all of the dust and all of the material that makes up the galaxies. And in the infrared, there's actually a really, really warm spot. You can't see a whole lot in visible light, but in infrared, there's a really, really bright area. And something is heating up the clouds from the inside. When galaxies interact, the clouds are swirled together and there's lots of turbulence. We believe that that turbulence allows gravity to start collapsing different parts of the cloud. And that collapse of gravity ignites a star eventually. So interacting galaxies may set off waves of star birth. It now seems that it's much more connected to the way galaxies interact and stars are born because of it. Infrared is also pretty interesting because we're discovering more about the inner structure of galaxies themselves. Here's a visible light picture of a beautiful barred spiral. And the Hubble Space Telescope took this little blue box is represented here. The Hubble Space Telescope took a visible light image of the very core of that. You can see the dust lanes going through the middle of that galaxy. And in the infrared, this is NICMOS, the Hubble's infrared instrument, you can actually see these little red dots are star clusters embedded in the dark dust. And you can see through the dust and see where the clusters are forming at the very heart of that galaxy. This is an infrared image of the very, very center of our galaxy. And this is the central 1 light year of our galaxy. Right where the arrows are is where we think the black hole is. And in the last few years, we've had some mind-blowing observations of stars being trapped around this black hole and actually being forced into orbits around it. But these are real pictures of stars moving around something that isn't there. We can't see it. And the black hole is there. But let's start again. Let me show you what some of these stars are doing. The animation will rerun. Okay, a lot of them are kind of whipping around this middle area. Pay attention to this one. I love this one. Okay, this star is coming in toward this region. Whoosh. That star got turned around and just thrown out back. These are stars being forced into orbits like comets. And they're getting progressively closer and closer to that central object, which is the black hole. This poor star here is actually trapped into a stable orbit. It's not going to escape. It's just going to keep going a little bit closer each time. But like I said, with infrared, we're able to look through the dust to the middle of our galaxy and actually watch these poor little stars stuck around that black hole. Okay, well, so that's about it. I'm going to end up now with a little bit of a talk at the telescope. The Space Infrared Telescope facility hopefully launches August 23rd. It's a relatively small telescope. It's just about 85 centimeters across with a mirror. The mirror is made of beryllium because the temperature it operates at is about 5 degrees Kelvin, so 5 degrees above absolute zero. There are 3 instruments that will do photometry, spectroscopy, imaging, all of that. We're hoping it's going to last for at least 2.5 years. That's dependent on the cryogen. The cryogen is liquid helium to keep it very cold, and the mission will really only last as long as the cryogen lasts. The observatory is actually going to be kicked out from the Earth's orbit. The Earth and the Moon area is really too warm. So we're actually just going to give it escape velocity from Earth and let it fall into its own orbit around the Sun. That'll get it far enough away from the Earth and the Moon for it to actively cool itself down and be able to operate. When the telescope launches, it's actually not going to reach operating temperature for about 2 to 3 months. So when you hear about the launch, you unfortunately won't see any data for a couple months, but we'll be working very hard on calibration.
Finally, Dr. Thaller shows us a great animation of the upcoming launch of the SIRTF facility on a Delta rocket and how the spacecraft will be launched to position itself following the Earth in its orbit around the Sun.
The telescope's going to be launched on a Delta 9 Heavy. That's a Delta with 9 solid rocket boosters. It's as big as they come. A little bigger than they were designed for, actually, because we need to kick it away from the Earth. There's a couple different stages, as you can see here. I didn't bring my speakers. There's a little bit of sound, but I'm certainly happy to speak over it. But these animations were done recently at JPL. Some of them are a little more interesting than others, but the launch sequence is always kind of fun. There was an amazing launch animation they did for the MER-B spacecraft. I don't know if any of you saw it. The problem was that they did this all timed to Lenny Kravitz's song, I Gotta Get Away. It was beautiful. And then they couldn't get the copyright permission from Lenny Kravitz. It was really, really unfortunate. Yeah, everyone dim the lights a little bit. The telescope's going to, the spacecraft, I should say, is going to have to go through a number of different burns to get into the right orbit. The really scary thing is that you've got to keep these heat shields oriented right. The instrument does not have any active shielding. It doesn't have any thermal shielding. It's only protected from the sun's heat by a heat shield, that must always stay pointed toward the sun. So that's going to be one of the scarier parts of the mission, is making sure that happens. Let's take it from another launch, obviously. Yeah, so there's the telescope getting itself into orientation. There's the heat shield. There's the telescope. The telescope is extremely simple. It's been redesigned many times to be very cheap, very simple. And like I said, it used to be a shuttle payload, but now it's an independent satellite. In fact, the only moving part on the entire telescope is the dust cover. It's going to come off. There's a pan. There's the dust cover. There it goes. That's the only thing that happens, so we have to highlight it. Yay! We're actually going to track that very carefully to make sure people don't keep rediscovering an interesting infrared object. You'd be surprised what you find in there. There's a nice pan around the spacecraft. Okay, here's a representation of the orbit. So we kick it off with escape velocity, and over time it gets a little bit farther away with each of the Earth's orbit around the sun. So it'll take it about 90 years to go all the way around and hit the Earth on the other side. This is what we call the death ray animation. I don't like it all that much. It's supposed to show how SIRTF takes observations, then points its backside at the Earth and beams it down. There it goes. Very nice. One of the engineers at JPL requested that, and then it gets information back up and goes on again. So, but it's kind of neat to see that you always got to keep that heat shield in the right place. It can maneuver and see the entire sky over the course of a year, but it has to keep the heat shield between itself and the sun. Here's a switch from visible to the infrared sky. There's the galaxy, the plane of our galaxy. That's real data taken by the IRAS satellite. You'll see that again in a couple more animations. Just to give you a sense about how full the sky is in the infrared. It's not a dark and empty place at all. When you can see all that coal dust, space all of a sudden becomes quite full. Yeah, there's a pan around the infrared sky. The center of the galaxy, in SIRTF's case, we're not going to be able to look right at the center because it'll be too bright. SIRTF is so sensitive, I don't believe it'll be able to look right in there. Okay, I think that's it. Great, thanks.
Thank you so much, Dr. Thaller, for such an incredible presentation. Although this month we've only been able to show highlights from the meeting, you can in fact view the entire meeting online at our website. And don't forget, you can attend our meetings yourself. They are held usually on the second Friday of every month at Chapman University in Orange at 7:30 p.m. See you there. The OCA maintains a special dark sky observing site far from the light-polluted skies of Orange County at a 20-acre facility which is about 30 miles east of Temecula, near the town of Anza, California. The facility is the home of the William Kuhn 22-inch telescope designed by one of the club's founding members. It is also the place where members, their guests, and the invited public attend monthly star parties. The 22-inch telescope is housed in an observatory building with a special roll-off roof. Let's join OCA President Barbara Toy as she opens the roof, ready for the night's observations. The following segment will give you a feeling for the 20-acre observing site and shows astronomers setting up their telescopes and getting ready for their observing that night. If you would like to visit the OCA's observatory, we do open the site to invited members of the public. All you have to do is ask. We even run special outreach events at this site for schools, colleges, and scouting groups. You can send your request to lookuptonight@ocastronomers.org, and we'll love to arrange a visit for you.
What do you think of Jupiter?
I think it's amazing. No, outstanding. No, I'm out of ideas.
Thank you so much for watching our program tonight. We'll look forward to seeing you next time